So this is kind of what you need to expect on an assessment. So it's not, I think this is the first time I've just handed you some probability problems and not said that it's under some subcategory, right? Like so far we've known it's basic probability, or we've known it's or we've known it's and ahead of time. But this is kind of where we're heading and where you need to start getting, like here's a problem, use your tools to get there, okay? So let's read this first one. There's 14 girls and 16 boys in a class. Ms. Carr randomly selects a student. What's the probability she chooses a girl or someone who likes math? Of course, in this class, it would be 100% who likes math, right? I know, it's not the favorite subject. Okay, what's your first question? Good. Which is it? Yeah. Remember that you can have some in. That was a seizure. Remember, some of these can have one embedded in the other, right? Like we saw with the shirt and the weather. So do read carefully, but this one is or. And then because it's or, what is our two questions? Or what is our one question with two answers? Yeah. So we've abbreviated that ME. And then what, just because I'm writing this right here, what are the two questions? What is the question for and? Good. Okay. So on this one, we are on or. And how about mutually exclusive? So again, the two things that we're trying to compare. So it says probability she chooses a girl, and then probability, like also including whether they like math or not. So what's the can be the same thing question? Okay, you're answering the question, but and you're right, but my question is, what two things are we saying can they be both?
Girl and like math.
Good, there you go. So good, girl and math, and yes, they can be that. So are you good with LM for likes math? How many of you are writing this out? Okay, I think it's really helpful to do that because it's basically a direct copy of your formula, so you know that it's set up correctly, and then we can just fill in numbers. All right, what's the probability of being a girl in this class? 14 out of 30, good. And then probability of liking math?
16.
Yeah, it's these two, right? So the 16 out of 30 like math. And then probability of being both.
30.
So probability of being a girl who likes math. That's what this both is. It's just the 9, yeah. Okay, and this one I think is good because it really shows why we're subtracting. Do you agree that those 9 girls are counted in this 14? So if we also count the 9 girls in the 16, they're getting double counted. So we pull those off that second round. So we get 30 minus 9, which is 21 out of 30. How'd that go? Okay. And you could reduce this. If we divide both by 3, we get 7/10, and now we know what percent that is, which is what?
7?
Yeah, that's 70%. Okay, you flip a fair coin. I always think it's funny. in probability, that's the only time you ever hear of a fair coin. Like whenever you flip a coin, do you ever think it's unfair? I sure don't. But apparently that maybe be a thing. So what's the probability it shows heads on the first and shows tails on the second flip? So that's our question. And which one is this?
And.
This is and, so we have to ask, is it independent or not? What do you think? Does one flip affect the other? Remember it's, yeah, okay. So it is independent, which means we can just multiply. And we're doing H and T. And then it goes on to say first flip and second flip. Does that confuse you at all? Like, does that bother you? Okay. Sometimes those bother me. Like, I start reading into it and think, does the order matter? Right? So do you think it mattered to the probability? And I should have said, in this case, do you think it mattered? The order doesn't matter. In fact, the probability would be the same if we reversed them. But sometimes it does matter. And that would be, I'll show you another couple after this, but if I don't pull it, when I pull it out, if I don't put it back in this case we're flipping a coin, so that's not really a thing, right? But we talked about marbles, or we had cards in a deck. Like if I take one out and I don't put it back, then what I drew first does matter, right? It changes the result after that. Anyway, what goes in between these two when it's independent? Yeah, it's just multiply. So this is 1/2 and 1/2, and so we get 1/4, or 25% chance. Guys, it's interesting on coin flipping how quickly the probability drops. Like if I said, what's the probability of flipping 4 tails in a row? It's really small. Like even that small of a number is really a difficult thing to do. All right, I want you to read these with me. I'm not going to say do them. Well, I might do on the second one, actually. But Tom has 4 navy socks and 6 black socks in a drawer. Does anybody put their socks in a drawer without matching them? Yeah, okay. Bailey has 4. One dark morning, he randomly pulls out 2 socks. What is the probability that he will select a pair of navy socks? Do you hear the difference in the wording?
Mm-hmm.
What is it? Okay, that's different, right? Like before, it was more explicit in saying first and second. A girl or likes math. Like it was very clear. The or ones usually are, honestly, but sometimes the and ones, like I told you yesterday, are not. So is this or and? It's and, because what is he actually, I want you to think through the very clear process. Like he pulls one out, and then what would you say? And he pulls another out, right? Like it's very, I don't know what the word is. Literal or like deliberate.
Hair kind of says that too.
Yeah, good. It kind of implies the and, right? Because to get, and it does it matter if he reaches in and just grabs 2 socks at once versus it's the same, yeah. Okay, something else about this kind of bothers me, and I'm wondering if it does to you too. We haven't talked too much about this, but I did mention this is without replacement. Do you remember me mentioning that? So he's not putting the first sock back because he wants to wear them. How does that change the probability process when you don't put it back in?
There's one less when you're going to grab more.
Yeah, right? So instead of, in this first one, there are 10 in there, and then when he reaches back in, there's only 9. So how do we account for that? I guess is the word I'm asking.
Pulling two at once.
Well, okay, so she said pulling two at once. It doesn't change the probability to think of it that way, but it changes how you work it because it's harder to think of. Because you could reach in and grab any two. It's easier to think of the probability of one at a time.
But you have to go through and subtract that one sock from the whole equation.
Yeah, so we take off what has happened, essentially. Now, sometimes for me, and I've told you that sometimes probability bites me, right? Sometimes for me, I'm like, well, how do you know he picked a blue sock first? And then how do you, like, if you don't know that, you can't address the second poll because now who knows what's left in there. Do you kind of see that, where I'm going with that? Okay. So you have to read into the request of getting a pair that, because here's where my mind goes. I'm like, here's a drawer full of socks, and I just blindly reach in. I may or may not grab a navy one on the first try, right? And if I'm blind, like I don't know, and I just have to suddenly open my eyes and match. Well, if I don't get a navy one, then I have to go back in and get two more. That's how my brain works, but that overcomplicates this. So try to not let your brain go there, and maybe your brain won't, which would be good. If it's written or worded this way, it's implying that the first sock was navy, because otherwise we're not making a pair of navy socks. We'd have to keep fishing, okay? Now, we can analyze that case later, but right now we're going to do it this way. So this is navy and navy. So that's how we're thinking of it, as one and then another. But this time, it's not independent. So without replacement is how we speak of the process, but the probability now is not independent. So what's our first probability? The first n is what? 4 out of 10. Then going back in on the second one, what is it? 3 out of...
He pulls out two socks.
No, he only pulls out one at a
Oh,
time.
he pulls out one, so it'd be...
So I've pulled out, this one is 4 out of 10. I pulled that one out. I'm holding a navy sock.
3 and a 9.
There you go. Now it's 3 out of 9 remaining. So now we can still multiply as long as it's like this, but we just have to adjust that second one. So this is 12 out of 90, which is kind of weird. But. Okay, so why don't you try putting this one together kind of like that. 2 glasses of root beer and 4 glasses of cola on the counter. We have 2 root beers and 4 cola. So the request here is 2 cola. So cola and cola. All right. We know it's and, but is it independent or dependent? Yeah. And I'm going to say not independent because we're going to use a different word. We're not going to say dependent. Well, we will some, but we're going to also add the word conditional. We're not quite there, I'm just going to tell you. But for now, this is the first C times the second cola. What's the probability of doing it once, the first time? 4 out of 6, good. And then how does that change on the second one? What was it?
3 out of 5.
Yeah, good. 3 out of 5. Okay. So we have to modify both the total and what's left over on that. 12 out of 30. Which we can reduce that. We could have reduced the other one. I'm just going to leave it. So this is kind of an early look at independent probability. Sorry, and probability that's not independent. This is going to go further for sure, and we're going to have a formula for conditional probability. This is conditional, but we're not quite ready to get into that. So I just want you starting to think, like, what happens if we don't have independence, okay? And see kind of how problems look when they're different. So that is coming. Grab that packet, please. And we left off with the ketchup on the fries problem, and I think we didn't have a chance to write it out, or at least I didn't. So just want to clarify and make sure everybody's understanding this one, because it seemed like there's a little bit of confusion on these area models. So remember, an area model is a tool that you don't have to use, but sometimes it's very helpful. When can you use an area model like this, like we can? What did we write at the top of page 4? It has to be independent. For it to be just like a straightforward use of this. You can get creative sometimes when it's not, but it really needs to be this kind. So, on this one, remember 25% of Americans put ketchup directly on their fries. Which, by the way, we didn't get a chance to ask Elizabeth. Do you ever do that? Put ketchup directly on your fries? None of us did that either. So. Anyway, so we set up a box and we kind of drew the dividing lines such that it looks like 3/4 and 1/4, or 75% and 25%. Remember that? And then we just found the area of each of these little boxes, depending on which one we are asked, by looking at the dimension. So remember, area of a rectangle is just length times width. In this case, you could maybe say height times width, because we're looking up and down. So like, what's the area of this, and what is the category of outcome in that biggest box? And remember, we're comparing our principal and our favorite celebrity. Who's your favorite celebrity? Joe Biden. He only has a few more days of work left. Wonder what he's going to do next. It seems like a job that you would just be so glad to be done with, to me. It's got to be so stressful. Every president that ever gets in that office, they start off with like normal looking hair, and then they're always gray when they're done. So if I was him, I'd be like, yes, I'm done. Do you have any idea? Favorite celebrity? Just for fun?
Wow.
I don't know who that is. Singer. This was Ariana Grande and Ryan Reynolds, Billie Eilish, Megan Fox, Ryan Reynolds. Ryan Reynolds, right? No. Dang it. Jack Black. Okay. And what did you say?
Wow.
It's a Spanish name? Okay. Is it a boy or girl?
It's a
Boy? Okay. All right. Well, what is this category of the no for what?
both.
For both. Yeah, so no and no would be this box. So what's the area? Well, the height is 3/4, and so is the width. So 9/16, which is a little rough, right?
I always do that.
What did you do?
For some reason, I can never comprehend that 3 times 3 is 9, and 3 times 2 is 6.
Oh, so did you make it 6?
Yes. I don't know why I do that. I've been doing it for like years now.
How funny. So the one that it asked about was that they both actually do. That was why I highlighted that one. And it's just 1/4 times 1/4, just the area of that little section. Good? All right, I'm curious about this next one. About 84% of Americans pour shampoo into their hand rather than directly on their hair. Like, right? So, let's do our survey. Does anybody put shampoo directly on your hair? I sometimes do. I'll be honest. In fact, I did this morning. So, how are we gonna? This one is saying the President of the United States. So we were just talking about Biden. Wonder how he did his hair
Doesn't really
today.
have any.
No, he didn't wash his hair. Did he?
Teacher.
Your teacher. Uh-oh.
Oh boy.
Yeah, and they both pour into their hand this time before putting it on their hair. So I'm gonna let you try. I do want you to try setting up the area model, okay? And then use it to try to answer that question. That's too big. So since both people are supposedly the same probability, then we can just split it in each direction the same way. And it doesn't matter which direction is who, right? It's the same for both. What if it did? Well, let me ask you that after we're done with this one. So the probability that both pour shampoo into their hand first. So do you see how this would be this big section, right? So both hand. So that's 0.84. Times 0.84. What if you did this with, instead of converting to a decimal, if you just did 84 times 84? You see how that would look weird? You could probably interpret what that actually means, but I think it's better to do a decimal. When we're working with or multiplying with decimals, or excuse me, with percentages, let's convert to a decimal first. And then we know it's 70.56%. It makes more sense that way. Okay, and then think about, we know, hopefully, it's starting to sink in, and probability decreases your chance, right? It decreases. But it's still pretty high, and it should make sense because 84% of people do it that way. That's a pretty high percentage. So even if we multiply it once, it should still be pretty high. Okay. I want you to note that all of this area model stuff is really just this. Like, time, probability of hand times probability of hand, which is 0.84 times 0.84 in this case. So it's really what we've been doing, isn't it? It's the multiplication rule saying if these are independent, multiply them together. It's just giving you a visual, that's all. So again, I'm not going to make you do this. I just think that it can be helpful if you get stuck, okay? And you'll notice like the next direction, say go back and do all these again with the multiplication rule. We're not going to do that. How do you feel about it, this area model? Does it seem good? Okay. What do you think happens if we have three things? Is it okay to just multiply all of them? Like what if it was flipping heads, 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 instead of just heads and heads? Is the multiplication rule still going to hold for 3 or more events? Yeah. Is there any reason it wouldn't? No. As long as they're all independent of each other. Okay. So let's look for a good one. Yeah, like here's one. So what's the sequence, what is the probability that a sequence of 7 flips of a fair coin turns out to be exactly this list? Okay? So let's do those two and then check, and then we'll jump down to this next one. And how long do you think 7A and B will take? Like, can you do it in like 2 minutes, like a minute each? Maybe 3? Actually, let's do 3 or 4. Okay. Okay, so we're trying to flip this specific sequence. And what's the probability of each one, of each outcome, I mean?
Heads is 407, tails is 6.
So, well, okay. I can see where you went with that. But this would be like saying probability of heads and tails and heads all the way across. So it's lots of and probability, right? Are the flips independent? They are, because one flip doesn't affect the other. So this is and then independent from there. So isn't it true that because it's independent, we can just multiply? Right? So what's the probability of heads? It's a half or 15, either one. It's easier, I think, to do it. Well, I don't know. You do it the way that's easier for you. Does everybody see where that's coming from? It's like an extension of what we've done with 2 things, that's all. As long as it's independent, it's okay to just multiply until you get all the outcomes accounted for. So this is, if you multiply a fraction straight across, it's 1 on top, because 1 times 1. And then it's 2 to the 7th power on the bottom, because it's just 2 7 times, right? Not 7 times 2, though. And 2 to the 7th, it's not a huge number. What was it?
128.
Thanks. 120. But what's the, like, in terms of percentage, what is the percentage chance that you will flip that sequence? Huh?
I got 0.39.
Yeah, it's teeny, right? 1, whoops, get all that out of here. So this is, oh wait, that's not what you said. So that is what percent?
Oh, wait, I did 8.
Oh, you did 8, wait.
Yeah, it's only like 8. Before it was 20.
Oh, I see, okay. So 0.78%. Is it gonna happen? It's pretty much 0, right? Okay. Well, what do you think is different about this one? It's like we had heads, tails, heads, tails, tails, heads, heads. Obviously, this is lots of tails and then 1 head. Does it matter? No, not in this case, because all of the probabilities are still 1/2 each, right? If this was some other kind of scenario where maybe we introduced a different outcome that has a different probability, then it would matter. But this is the same. It's 1 out of 128. Yeah, it's still 7. So. Okay, so big idea with those, you can multiply as long as you're still dealing with independent probability. You can just multiply all the way across. Okay, how about this one? And then I want to show you the tree, and then let's see where we are with that. So this is homeschool versus public school. Public school living in a small town, and then we do homeschool. 27.9% of public school students live in a small town. And it says if you select 5 students at random, that would probably be like nationwide. Just pick randomly 5 kids. What's the probability that they all live in a small town? So we're not going to take time to do it. I just want you to say what you would do. So probability that they all live in a small town. If we just randomly pick 5 students from our country.
Turn a percent into a fraction.
Ooh, you would?
Turn a 27.9% into a fraction.
To a fraction?
Or a decimal.
Which one is easier?
Probably. Fraction.
Okay. For me, I think decimal, but because this, as a fraction, do you know what it is? Okay. As a decimal, do you know what it is?
2.79.
Move it once more. It's always 2. With percents, you're always moving it twice.
So 0.27.
Yeah, so see, you got that one. As a fraction, it would be 279 out of 1,000. And then you're multiplying that 5 times. That would be a kind of ugly thing, right? Does everybody agree? Each kid is the same probability, right? Since it's random. So we would just do this 5 times. Okay. Go ahead and do that on your calculator. 0.279 to the 5th, or you can count 5 of them. I would just do 0.279 to the 5th, though. Not times 5. That is not the same thing. Okay, here's what I'm saying. I would not want to sit here and do this. I don't even know how many I've done. I think I've done 4. That's 3, 4, yeah. And you see, I'm like, oh, I've lost count because it had to scroll. The actual calculator did. So now it's, and then I mess it up, like, of course. So this is a pain. Here's what I mean. If we just do 0.279 and then take our exponent button to the 5th, since we're multiplying it by itself 5 times, that's what 2 to the 5th power means. And then we can do it in one little calculation. It's just cleaner. What percentage is that?
0.169.
Yes. Is this very likely to get 5 right? Okay, good. You can see, I think, with these last few examples that and probability really tanks the chances, right? Because this is only 5 kids. It's not even very many. All right. I think we're good on that. Do you? I think we'll come back to this maybe and do it as a warm-up. Because I want to have a chance to show you the tree. Okay, I'm curious to see if any of you will like this better. It's basically the idea of a visual representation of probability like the area model was, only now it's the tree shape, kind of visual. Okay. The downside about trees is they get big quick. So just know that's going to be true. So here's what this is saying is create the tree. I'm going to do that with you. It says each G means girl and B means boy for having the gender of a kid, right? When it's born. So in the United States, the probability that a girl is born is approximately 49%. So it's just under half, which does change the number, right? So here's how this will set up, and I want you to do it with me. You can do your tree up. I usually do mine sideways. So we have our first kid. How are we going to come from our original or origin point? How are we going to come off of that with our diagram? Think of how we did it with the pizza or the sandwiches or whatever. Yeah. So we'll just make 2 branches. Try to make them kind of spread out because, we fill in sometimes from there. Okay, here's the thing. We're not just counting outcomes this time. We need to label what they are, of course, just like always. But this time we need to add the percent chance of each one. And of course, always do that as a decimal. So 0.51, 0.49. Where'd the 0.51 come from? Because it didn't say that.
It's the remaining 100%.
Good. So that adds to 100%. Okay. So let's say we had a boy first. What's the next, like what do we do for the next kid? Same thing, right? And we label it boy and girl and same probabilities. So 0.51, 0.49. But if we had a girl first, how about that direction? Does it change? No, it's the same. So our next kid could be boy, girl. Now, one thing that I would recommend is, it's not critical, but it's probably helpful. Notice how each branch I'm doing the girl on the top and the boy on the bottom. And it's not critical, like I said. If you switched it, it wouldn't be an issue. It just keeps you organized, I think, in a better way. Okay. All right, why don't you finish this off with one more layer of kids? Because down here, I guess you probably didn't read ahead, but we're doing 3 children. So we need one more layer. A says we're having 3 kids. So what's the probability that a family of 3 will consist of 2 girls and a boy? Not necessarily born in that order. We just want 2 girls in the family and 1 boy. How will you use this tree diagram to do that?
So go down the road path, like go up and down again.
Okay, so he said this. Like that, and then down the boy path. Right? So that would be girl, girl, boy. Is that the only one? No?
Also do boy, girl, girl.
Okay, so boy, girl, girl. There should be another one.
You could do girl, boy, girl,
There you go. Girl, boy, girl.
and then,
I think that's all, isn't it?
Boy, girl, boy.
Well, that would be 2 boys.
Oh.
We want two girls. I think that's all. Alright, well now what?
plug in the percentages, like, take the percentages from each of those and then add them all together.
Okay, so she's proposing, find the, like, maybe I should have done different color of pathways here. So find the probability of each pathway to getting 2 girls, and then she said add them. What do you think? Is that okay? Because we've been doing a bunch of multiply for and probabilities. This is an and probability because it's girl and boy or whatever. So is it an addition or an add situation at the end of all that? Think hard. Adding would imply that it's or at that point, right?
And then multiply, and then
So let's rephrase what Bailey said in terms of our either and or. Do you agree this is girl sorry, this is boy and girl, so definitely down each colored path would be multiplication, right? But then isn't it green or yellow or blue? At that point, isn't it or to get there? So, was she right? She was right. Good job. You just kind of knew it. Okay? So why don't you go ahead and figure out the probability of having two girls and a boy? Let's check. So do you guys agree that the probability of each colored path is the same? Okay? So if we just multiply probability of girl times probability of boy, and I'm just picking one, this is the yellow one, times probability of girl again. Okay, that gives us one pathway, and then what do we do to get the total?
Once you're done multiplying each path, and you multiply them all. Or, sorry, not multiply, you add them.
Add them, yeah. This should be like roughly 0.12 or so, right?
Yeah.
Yeah, 0.1. Let's just go with 1.22. 0.122. Okay, and then we just add for all three. Let me write this first. Per path. And then for two girls and one boy, it's 0.122 plus 0.122, etc. So you have a pretty good chance. Is that 366, right?
Yeah.
Okay. 0.366 or 36.6% chance. Less than half, but not as bad as some of these and probabilities we've seen. Because we stuck that or in there, right? Increased our chances. Alright, how are you feeling about and probabilities that are independent? Okay? Do you feel like you need anything else in terms of example in your notes? My personal thought is not, because we have this whole packet. Remember, on a note card, you can't put examples anyway. So just keep this packet handy. But if there's something, like a little tidbit that you want to put in there, I'm happy to help you out with that. Any thoughts on that? On the sheet that we worked on with or probability, this one, why don't you grab it? And why don't you circle 11? $21. That's kind of like the socks. And then flip to the back. 24. And we'll stop there. So 11, 21, 24.